Okay, Bismillahirrahmanirrahim. Assalamualaikum and a very good afternoon. So welcome to SEEE 2073 Signal and Systems. Okay, today we are going to discuss different types of Fourier transform properties. So these are some of the properties. So you need to have your Fourier transform table or Fourier transform pairs in hand. Okay, let's look at the first property of Fourier transform, which is time scaling. So if you still remember, if there's changes inside the bracket, so it is time-based operation. In this case, the signal being scaled by A in time domain. So what happened in frequency domain? The signal in frequency domain, V omega, being modified in amplitude and also in frequency. Okay, if you refer to the Fourier transform table, so if you have a signal being scaled by A in time domain, so the Fourier transform or the signal in frequency domain being modified in amplitude and also in frequency. Okay, just a recap. In time domain, if you have A larger than 1, the signal will be compressed in T, but in frequency domain, the signal will be expanded in frequency. But if you have the scaling factor less than 1 in T in time domain, so the signal will be expanded in time domain but being compressed in frequency domain. Let's look at the first example. If you have Vt equal to A rectangular T over tau, so refer to the table. So the Fourier transform of rectangular signal equal to A tau sinc function omega tau over 2. So now you have a new signal V1t in which it is from the original signal Vt, but the signal being scaled in time by 2. Okay, so you need to refer to this table again when you have time scaling. So what happened in frequency domain? So this is equation 1, the original signal. So now you need to work on the new signal. So in this case, V1t is equal to V2t. So in Fourier transform, it becomes V1 omega, in which it is equal to 1 over A, the scaling factor, in this case, A equal to 2. So 1 over 2. So this is V, so V omega over A over 2. So what is V omega? V omega is from the original signal. So this is your V omega. Okay, so in this case, we call this equation as equation 2. So you need to replace 1 into 2. Okay, so 1 into 2. Now your V1 omega, V capital V for frequency domain equation, V1 omega equal to 1 over 2. And then what is your V omega? So now replace V omega using this equation. So it is equal to capital A tau sinc function omega tau over 2. Okay, so but if you notice here, all omega will be divided by 2, meaning that this omega will be divided by 2. Okay, so now simplify the equation. So V1 omega equal to 1 over 2. So A rectangular, so A tau sinc function omega tau over 4. So this is the Fourier transform of the new signal V1 omega. This graph, this is the original signal. So the rectangular signal, so A rectangular T over tau. So this is your tau, the width of the rectangular signal. So it produced the sinc function. Okay, it is equal to A tau sinc function omega tau over 2. So what happens if you have the scaling factor a larger than 1 in t? For example, you have VAT. So if a is larger than 1, so by theory, the signal will be compressed. If you compare this signal to the signal will be compressed in t, but it will be expanded in frequency. So this signal, this is the original, becomes, you can see that the frequency being expanded from the original frequency. Okay, let's look at another example on time scaling. So if you have an equation Vt equal to Ej 2000t and Rt equal to V minus 3t, so obviously you need to refer to the table for the first function, the basic equation. So in this case, you have your Vt equal to Ej 2kt, so in which you know that your omega naught is equal to 2000. So therefore, your V omega equal to 2 pi del omega minus your omega naught 2000. Okay, so next your RT equal to V minus 3t. So obviously you will notice that the signal being scaled in t by a. So in this case, your a equal to minus 3. So again, refer to the table. For time scaling signal, so it is equal to this equation. In this case, your a is minus 3. So in this case, your RT is equal to V minus 3t. So in which your R omega equal to 1 over a. Your a is minus 3. And then V, because this is it dependent on V, so it's V omega divided by a. A is again minus 3. So what is your V omega? V omega is this, the fundamental equation. So replace the fundamental equation into R omega. So R omega equal to 1 over 3. What is your V omega? It is 2 pi del omega minus 200. So from here you notice that all omega will be divided by minus 3. So in this case, your omega divided by minus 3 minus 2000. Okay, and then simplify the equation. So this is the Fourier transform of RT or R omega. Let's look at the next properties, frequency shift or modulation. This is the basic function, Vt equal to V omega in frequency domain. So if you have a signal Vt being multiplied by exponential function, so in frequency domain the signal will be shifted by omega naught in frequency. Same goes to when you have the signal in time domain being multiplied by cos or sine function, so the signal will be shifted in frequency domain as well. Okay, and this is called modulation process. So this is the function from the table. Okay, let's look at the first example in modulation or frequency shift. So find the Fourier transform for the signal gt, meaning that you need to get the j omega given by this equation, where ft is given by 2 rectangular t. Okay, so basically when you have all equations, so you need to refer to the table. So ft will produce f omega. So in this case, for rectangular function, it producing function in frequency domain. So compare the given equation with the one in the table. So you have your 2 rectangular t over tau. In this case, t over 1. So your tau is 1. Okay, so in this case, it will produce your capital A is 2, your tau is 1, sinc function, omega tau is 1 divided by 2. Okay, so this is equation 1. So now to solve for gt to get j omega, So it is a multiplication between the signal with cosine function. So this is frequency shift signal or modulation. So you need to refer to the table. So for this function, it will produce this equation in frequency domain. Okay, so in this case, your Gt is given by ft cos 20t. So if you compare to this equation, so you'll notice that your omega naught is equal to 20. Okay, so g omega equal to this, in which omega naught equal to 20, positive 20. Okay, so now the equation is 1 over 2 f omega minus omega naught. It is 20 and plus f omega plus 20. So what is f omega? F omega is from the first equation. So replace f omega into g omega to get the final answer. So in this case, your f omega equal to a sinc function, omega over 2. But please look at this equation. All omega will be deducted by 20. So omega deducted by 20. And on the other side, it is being added by 20. Okay, so divided by 2. So and then simplify your equation. So GT originally a signal FT in rectangular. So this is, you can see the rectangular shape. Multiply with cosine function. So you can see that cosine shape inside the rectangular. So in frequency domain, the signal will be shifted in frequency, one on the left and one on the right. Okay, let's look at the next Fourier transform properties, convolution. If you can recap this term convolution from the first chapter, so it is kind of difficult to solve the convolution by using time domain signal. However, it can be simplified by using frequency domain signal, in which if you have a signal V1t into a system, so here you have V2t, so the output is V3t for example. So in this case, V3t is equal to V1t convolve with V2t. But in frequency domain, you can solve this convolution by using multiplication of both signal in frequency domain. So in this case, V3 omega equal to V1 omega multiply with V2 omega. Okay, if you have a multiplication of signal in Fourier in time domain, so it will be a convolution in frequency domain. If you have convolution in time domain, so it will be frequency multiplication, it will be signal multiplication in frequency domain. Let's look at an example on convolution. So you need to find the output ft, meaning that the final answer must be in time domain equation. So given f1t equal to e minus at ut and f2t as shown. So as usual, to perform Fourier transform operation, so you need to refer to Fourier transform table. Okay, you have the exponential function in this case. So in both cases, the a is 1. So if you have this equation, meaning that in this case, you have your 1e minus at ut. So this is your f1t. So your f1 omega equal to your a is 1 divided by a plus j omega. So the power is positive a. Same goes to the f2. Okay, so next you need to perform the convolution. The convolution in time domain will produce multiplication in frequency domain. Okay, so now you have f omega equal to f1 omega multiplied with f2 omega. So f1 omega is this equation, and f2 omega equal to this. So multiply both signal, so you get the f omega. So this is f omega. But the question asks you to get the output in time domain. So you need to do inverse Fourier transform to get ft. So compare back this equation to the table. So you'll notice that it is in the same shape as this. So the final signal, the inverse Fourier transform, produce ft1b minus a, in which this one is equal to e minus at ut minus e minus b t ut. Thank you.